welcome to our talk today. We're going to do a brief talk on Lenz's law and discuss an experiment that we did relating to Lenz's law. So briefly, just to give you some background on Lenz's law. Lenz's law, the main theories behind the project are two laws, Lenz's law, Faraday's law. Both laws are related. In fact, Lenz's law is incorporated into the equation of Faraday's law. Lenz's law is named after the famous physicist Heinrich Lenz. That was formulated on conservation energy, the common way of understanding. It assures that currents are also known as the eddy current. If the magnetic field strength is varied, that will also create magnetic flux generating induced EMF. Okay, so I hope you learned something from that. Going through the physics of Faraday's law, we know that the induced electromotive force is proportional to E divided T. In the above equation, we know that N divided T is induced electromotive force in volts. Okay, so if you Faraday's law expresses the project is based around all of these things. Okay, so hope you're able to read what's happening there. The string providing oscillatory motion in the vertical direction for, that was the spring, that thing there, and that was the magnet, and it was going up and down. And this is the photograph. I didn't realise we had a photograph this good.
Yeah, no, it's pretty good.
Oh, okay. Anyway, so as you can see there's a magnet there, and we had this thing going up and down there, and it worked. Okay. So according to the method, what we did is we held the spring on the retort stand tightly so the spring doesn't slide during oscillation and connected. Find the ways to reduce discrepancy of errors. Okay. So I think now Angus will take you through some of these results that you can see there on the board. Thanks.
So what we did was when we got the experiment, we found a bunch of values. And we got velocity, error, potential, the error in the potential.
It was in this one here.
The current and the error in the current, this one here. And I mean, you guys can all see that we got numbers that were pretty good, actually. So yeah, that was really good.
Especially the one in the middle.
Yeah, the potential came out really well. So we just got a graph here that you did, so I'm not actually sure what it is.
It's voltage with respect to velocity, I think.
Yeah. And here's the equation.
That's velocity on the bottom there.
Yeah,
that's voltage on the side.
Cool. And so we plotted this just in Excel with error bars, like we've been doing all year.
Oh.
So that was.
That equation up the top there, that should have been down the bottom.
It's a bit cut off, but it says 0.191x plus 0.001.
And it works.
It works. So that's pretty accurate.
And it's linear. Can you see? It's linear.
So that's what we expected from the theory that we did. And now we got current, so it's pretty much just the same thing that we did. The velocity should be.
And we had a magnet. The magnet had a velocity. Did the magnet have a velocity?
Yeah. It was.
Oh, yeah. Sorry. Okay.
Wasn't it?
Yeah. That's spring thing.
Sure. Yeah. The spring with Anyway, so we got and then so these are our results. Oh shit. These should be Q's. Something's gone wrong here. These should be. I'm pretty sure these should be Q's. I'm not sure.
I think that was supposed to be the current. No, maybe it's the.
No, epsilon.
It's that defy.
Defy. Yes. Yeah. Defy. Okay. So these little REs should be defy. We probably did that. Anyway, so what the results were was, as explained in the theory, the relationship between the voltage generation and the velocity was d phi equals NBVL, where the d phi was, it should be V, it's because it's voltage, potential difference in volts. N is the number of turns, B is the
that's velocity.
V, it says here voltage. V is the velocity of the magnet in meters per second, L is the length of the coil in meters, and now based on the analysis we got L and LB equals 0.206 Tesla meters, which was almost near 0.191 measurement, which was obtained as a gradient from the graph of voltage against velocity. This verifies the above equation and proves the direct relationship. Along with voltage, the current is also direct proportionality with the voltage of the magnet, the velocity of the magnet, and the graph of current versus velocity of the magnet has slope 0.257, which was from the equation that we did on those plots.
And it was right, because it was linear.
Yeah.
It was linear.
So we then sort of did a discussion, and what we pretty much, I mean, I'll just skim through what we've got. We pretty much found that the magnetic field increased the number of oscillations made by the magnet attached to the spring, dampened faster when the magnets had fewer magnetic fields. Yeah. There was an increase in voltage, there was an increase in current, and the dampening process progressed. The instantaneous voltage and current reduced. This shows one of the signs of direct proportionality between voltage, velocity, and the magnet and the voltage generated.
And therefore we must have EMF.
Exactly.
See? It's really simple. That's it.
The bar magnet was not good enough to generate
electromagnetic
or electromotive force.
No, it's definitely. Is it electro?
Yeah.
What didn't we do this in this experiment on magnetism?
No, it's electro. It's electro.
Oh, okay.
This is
Electronic.
Electromagnet. Yeah.
Electronic.
So the rare earth magnets were smaller in size and weight, and that made it impossible for oscillations to take place. Therefore, the long, thin, heavy iron rod was attached to the rare earth magnets, and the springs provide oscillatory motion in the vertical direction. So again, it's just up and down. So, yeah. Then we got conclusion. So the main results we've divided into two parts: the graphical interpretation of linear trend between voltages induced in the current and the velocity of the magnet, and as you guys can see, the comparison between the theoretical value and the experimental value of the
That's definitely a magnetic thing.
Yeah, phi.
We worked that out already.
Which verifies the equation d phi equals NVLV. So the above results help in achieving the aim of finding the relationship between the velocity of the magnet passing through the coil and the voltage.
And it was definitely linear, so we got it right.
Linear. Good work. So we did well.
Thank you.
That's it.
Okay, welcome to our talk on induction today. Just to give you a brief background on induction, so you know what our experiment entailed and so forth. Initially, according to Faraday's law of induction, we know that a change in flux should give us some sort of proportional EMF, and therefore resulting in some measurable type of current. According to Lenz's law, we need to make sure that we add that negative sign to the equation. So as you can see there on the board, the EMF is equal to minus n, which is the number of loops that you're dealing with. If you're dealing with a coil, multiplied by the change in flux over time. Okay, and we should be able to measure some sort of measurable current or induced current. Okay, so just taking you through the experiment. There on the board, you can see we set up an apparatus. If you look up on the top right-hand side of the screen up there, you'll see an actual photograph of the experiment that we were running. We also had it connected up to the Logger Pro, which is the blue device that you can see right up in the right-hand corner there. From that device, we were able to measure a current, okay, and predict whether there was some relationship between the EMF and the change in flux over time. Okay, so these are the results that we measured. As you can see there, we've got a plot. We've got a plot there of voltage versus velocity, and what we found was that yes, in fact, after laying all these results down and interpreting all the results, we were able to, in fact, establish that it was a real linear relationship between the voltage measured and the velocity of the magnet passing through the coil, which led us to believe that the relationship was definitely linear as predicted initially in the pre-work. Okay, so Angus is now going to run you through the rest of the results and talk a little bit about the errors. Okay, thank you.
So what we did in terms of the experiment to make sure that our experiment was reliable as well as accurate was we made sure that we didn't just take, you know, 1 or 2 results and just throw the numbers in and see if we got out a straight line just from the points and the numbers. What we did was we actually did a fair amount of error calculation and a large number of modifications to our original plan for the experiment to make sure that we got good results. And one of the ways you can see that is through the plot that we've got here. You can see that the error bars on each plot, on each point, aren't actually the same. And the reason they're not the same is because we didn't just use one sort of, you know, 5 millimeters or, you know, 5, you know, units for voltage and velocity as our errors. We actually went through and did some detailed calculation from the apparatus we used. Now what we figured out, was that using the apparatus that we had, we could constrain our errors by increasing the number of turns, for example, would decrease the error in the analysis. And so that was one way that we improved our experiment. And so what we did then was we took our points with our errors, plugged them into some plotting software, and we got out our relationship. And there's 2 reasons that we can say with a fair amount of confidence that this result is pretty good. The first one is because theoretically we expect the result to go through 0, right? 0 velocity, 0 voltage. And what we can see is that our line passes through 0 to effectively 2 significant figures, which is pretty good, and we're pretty happy with that. So that's one way that we can tell this is a really good result. The second reason is that when we don't have here, but the grouping of the points, as you can see, all lie very consistently with the linear fit. So that's also very good in terms of our results. We also did this for another plot, which was current with respect to velocity. And as you can see again, we got some very nice data and some very, you know, good results. So we're very happy with these ones as well. By very similar methods, we did a fair amount of adjustment of the actual experiment modification to make sure that our results were reliable and were accurate. And that's how we got our result. So that's good. In terms of the discussion of results, what we did was once we got our slopes and once we got our values, we then just simply plugged in the raw values for the slopes into our equation, as you can see here, to establish a trend for the value of E. What we did also was do the same calculation with our errors to get an idea of the error on E, and therefore also improved our result in terms of determining whether or not there was a linear relationship. So what we need to think about now is, in future, what could we have done, or what should we do to make this better? So how could we have improved the experiment? And the way that we could have improved the experiment were, firstly, and probably most obviously, by just doing more work. Now obviously we were constrained by the lab times, but we did do a fair number of repetitions, and we think that that was okay. Obviously the more number of repetitions that we do, the more analysis and the more reliable our results can be. Moreover, if we use devices which have less error, so if we could, I don't know, get superconducting wire, for example, with no resistance, then that would also improve our experiment. But obviously we're limited by the first year labs equipment. So that's pretty much how we got our analysis, how we got our result. We think that the result has been very accurate and very reliable in terms of getting a linear relationship of E, and therefore we think that this experiment has been a very good success.